All right, so welcome to the mid-program presentation, where we have three teams here who have been working on developing their own Canvas, kind of learning about it. Basically, I don't think really anyone had any introductory knowledge to it, so learning obviously how it works and then getting to actually physically build it, all in a virtual setting. I think it's been really cool. It's been cool to see kind of I've been monitoring some of the team chats and seeing everyone's progress, asking good questions. And yeah, so this is a mid-program presentation where they'll be kind of giving everything that they've learned, presenting it to the team here at Modine, as well as the Internship on Demand team. And yeah, as far as kind of rules, I wouldn't even say rules go, but presentation should be around 8 to 12 minutes each. I'm going to have one teammate share their screen for the presentation. Going to go just walk through the teams, team 1, 2, and then 3. Make sure to have your camera on while you're presenting. We're recording the meeting. And then I do have a survey for kind of feedback on the presentation, which I'm going to send in the chat here. And it essentially has a questionnaire of kind of how each team is doing. Obviously, if you're presenting, you don't have to fill it out for yourself, but we'll have some time, about like 3 minutes after each presentation, for all the students and all the mentors to kind of go through and grade each team. And then after that, we'll move on to the next one.
Awesome. I'm going to jump in here quick, right?
Yeah.
So just to piggyback on that, so we're asking, obviously, our Modine mentors, the team, you guys are scoring and working on those surveys. But for our fellow students, please complete that survey for your peers. We'll make sure we pass along any feedback presentation-wise. So for our final presentations, everybody kind of knows what areas they should be working on or what worked well, right? So please make sure you all complete those surveys for your fellow cohort mates. It's a really good way for us to get feedback and then pass that on to other teams. So thanks, everyone.
Awesome. So without further ado, team 1, Avanico, Samuel, and Adam.
Okay, I'm going to share my screen. Okay, first I would like to say thank you to the Internship on Demand team, as well as the Modine team, for giving my teammates the opportunity to work on this great project, as well as taking the time to witness our midterm presentation. My name is Samuel Oladeji, and I am a senior student at Minnesota State University, Mankato. I am majoring in automotive engineering technology, and I'm expected to graduate December 2024. And here with me are my other teammates.
Hi, my name is Avanico, and I'm a mechanical engineering student at the University of Pennsylvania, and I'm expected to graduate in 2026.
And my name is Adam Holmes. I am a mechanical engineering student at the University of Iowa, and I will be graduating in May of 2025.
Okay. So we know the future of transportation are electric vehicles. And electric vehicles have three major parts that make them function and distinguish them from the internal combustion engine vehicles, which are the electric motors, the power electronics, and then the battery packs. These three systems need to be thermally managed in order for their temperatures to be optimized for the highest efficiency possible. And that is why this project was involved in understanding the thermal management in electric vehicles, as well as building a controller area network that facilitate the communication and the proper operation of the thermal management system. The thermal management system comprises of series of microcontrollers and electronic control unit that allows it to manage the temperature of the three systems I mentioned initially regarding the electric vehicle, as well as to cool them and heat them respectively, depending on the environmental condition.
So once we had our objectives set for this project, we researched a bit more about how CAN bus systems work and some of their real world applications. Then using the parts that we received at the beginning of the program, we soldered our own transceivers and teensy board. It was pretty straightforward, just through hole pin soldering. And then we validated that our solder joints were working correctly with a simple LED program that tested the teensy board. We continued to validate the provided code as we started prototyping a CAN bus system on a breadboard, where we integrated 2 transceivers and our teensy and tested the communication and data transfer between them. And we validated the code that was provided to us as well, and made a few changes. And then finally, we created a schematic in KiCad, which we'll show later in the presentation.
So along this way, we faced a few challenges, and one of the main ones was that integrating the third transceiver into our system. So we had a good amount of success with the first 2 transceivers, and we were able to get our CAN bus system working. But with the third transceiver, we were unable to figure out how to sort of get pin access, given that there was only CTX1 port and CRX1 port, or 2 of them, and CTX2 and CRX2 on the TNC. So we had a bit of trouble with this, so we decided to just stick with 2 transceivers, and we moved on from there. The second challenge that we faced was more minor, but it dealt with the actual package that was provided to us for the code, and it had to do with the error frame, and we were actually unable to get our error frame messages to send because we didn't have access to the package. And a third and more minor issue that we actually ended up resolving was the issue of timestamps. And so for this, Adam actually integrated a solution that we will go into a bit more detail later. But originally, we were unable to get the timestamps to appear on our serial monitor.
So here's some pictures of our schematic that we ended up creating. So as you can see in that central image, that's the breadboard prototype that we made of our CAN bus system. And it's a very robust design. We have color-coded wires connected between the different ports, so we know what's connected to what. And that made it a lot easier when we transferred it to KiCad, where we created the schematic. And it's a little small, but in the bottom left, we have bypass capacitors, which are connected to the transceivers. In the transceivers that we actually that we received, they already have capacitors built in, but we needed to add them separately into the KiCad. And these just reduce noise and make the data more consistent. And then there's also 2 terminating resistors, which take out any remaining voltage in the system and ensure continuous uninterrupted signals as the system runs. So from the bottom left circuit diagram, we were able to then design the traces on the PCB, which can be seen in the top right image. And from there, we created a 3D render of a PCB that could actually be manufactured, which is in the bottom right.
And of course, our schematic and CAN network design is not complete without coding the TNC and giving instruction to what it's supposed to do. The controller area network is supposed to facilitate the communication between the different modules and controllers in the thermal management that receives feedback and information from the sensors to make it tune the major components that measure initially for better optimization and operation. And so to code our TNC, we first of all assign the output power pin, which is going to facilitate the output message. And then we set the parameters at which we want the message to be communicated. We set the transmitter, the receive buffer size, and the transmit buffer size. We also set the baud rate at which we want the serial monitor to output message to us, as well as the baud rate for the CAN networks as well. And then we assign IDs to each message of the CAN system. That way we can identify each other from them and facilitate troubleshooting as needed.
So as Ivanico mentioned earlier, we had a bit more that we added to the code. And one of the problems that we were having was with the timestamps in the serial monitor, which turned out to just be a simple checkbox that you can enable and disable. But it's something that's very helpful for when you're testing and debugging the code to make sure that you're receiving signals at the correct time and there's the correct amount of delay. And so because we didn't have this enabled, I wrote a simple loop that basically just acted as a counter, and it counted the time between signals in seconds, and it just output the time with the data that was being sent. So just a quick fix, but we ended up resolving this anyways.
Yeah, so our latest step was basically putting together a bill of materials for the prototypes, and we identified 5 basic components that were needed for this, and those are the actual TNC board, the printed PCB, CAN transceiver, and then the resistor and capacitors. So we put together this bill of materials, and our final total for 10 prototypes came to around $320, with a theoretical start date of October 12th of this year. And so some of the applications for our design of this CAN bus are similar to Modine's actual thermal management systems. So we talked about this at the beginning of the presentation, that some of the main things that Modine focuses on is heating, cooling, and power management. And these 3 systems sort of need like different sensors and actuators to work together so that they're transmitting data between each other and have systems functioning properly with the vehicle and interact with the user input as well. So we use the ISO 26262 standard to basically kind of come up with some safety systems or to implement ways to prevent hazards and malfunctions within these systems. And a few ways we identified to do that is using, one of them is the serial monitor. And basically by using the serial monitor to provide direct data input into our program, we'd be able to sort of debug some of the issues that come up with each microcontroller unit. Another one is error frames. So ensuring that we have error frames that are communicating the proper like error messages to all devices connected to the CAN bus system is super important to upholding the standard, because that way we would have more communication in the case of failure. And the final thing that we identified is the redundant safety systems. So having multiple backups that are able to basically shut down in the case of failures of other components is really important, because even with error frames in place, we need some kind of way to like mitigate the hazards associated with them. So they actually have to act on that. And that's why implementing redundant safety systems is super important. And we did this, all these are kind of in mind with our specific 2 transceiver implementation.
And moving forward, we plan on integrating 2 extra transceivers into a CAN bus schematic system, as well as conducting safety testing on the CAN bus scanner to ensure that it's communicating as it should, as identified by the ISO 26262 safety standard. We also plan on making market research and product research regarding other scanners available out there to be sure that our product is meeting competition as well as breaking records. And we also plan on working on the optimization of our PCB layout to better fit the design of our application. And this will be the end of our presentation. We appreciate your time. And then at this time, we welcome any question if there be any. Thank you.
Yeah, this was great. Thank you. I do have a question for you. You're talking about PCB layout optimization. What are your plans there? What areas do you think you have for improvement?
So we plan on arranging the wires, because apparently the way we design the PCB itself, due to our limited knowledge we have with working with the key card and the design, we just kind of connected things the best fit, and some of them we are not really sure if it's the right way it's supposed to be due to the time we had to prepare. So moving forward, we plan to look at other PCB layouts from other scanners, as well as other available resources we can use to learn, to be able to design our PCB to be professional and robust as much as it can be.
And going off of that, one of the major things that we want to change is currently we only have traces on one side of the PCB, because as Samuel mentioned, with our limited knowledge of the program, we didn't know that how to access the other side. So that will help with efficiency a lot.
Okay, great. Good answers. I'm really impressed you've got ISO 26262 on here. What what got you started on looking at functional safety standards like that?
So we know that in the world today, there are a lot of regulation that have to do with car systems. And that's because of hazardous situation. If they're not safety standard to ensure that the systems are working properly like they should, you could have a situation where a car lights on fire, or maybe a car suddenly just is not working, like situation whereby you have the pedal stuck on and the car just accelerates continuously. So the ISO standard is to ensure safety in the system and ensure that every system are working like they should. So there's usually a rigid protocol and steps that each product and design usually have to go through, as specified by the ISO 26262 before it is being allowed to be used.
All right, good answers. Thank you. That's all the questions I have. Anyone else on the Modine team have any questions?
Go ahead, Steven.
I'm not gonna lie, I hit it on accident. I'm sorry. I had my mouse there and then I went to grab and I clicked it.
All good. Well, awesome. If there's no further questions, for those of you who were viewing the presentation, be sure to take a minute or so.
I do have a question, Ryan. Sorry.
You've got a question.
Sorry. I know. So Samuel, Ivanico, Adam, nice job, guys. Now, none of you are electrical engineers, so you're all. I know Samuel, you're automotive engineering. Adam, Ivanico, you guys are mechanical. What was that experience like? Kind of having the background in mechanical, now working a little bit more on the electrical side of things.
Okay, I can answer first. And as an automotive engineer, I have worked on a series of modules on my own car personally, as well as some other project that I've worked on in the school. So while working on this CAN bus system, I actually got to learn how the different ECUs and modules that are in my car and other projects I've worked on, how they actually communicate with each other to ensure that they are all in synchronous and giving feedback loop for operation, for standard operation like the ship. So that did help me learn a lot, even more about programming, as well as developing an understanding of what a CAN bus system is and how it's actually the major nervous system in a car.
I can go next. So, as a mechanical engineer, I don't have as much background in electronics work. I've done some soldering and breadboard stuff before, but I've never designed my own PCB, and so I really enjoyed that. And this pre-internship has opened doors to new things that I'm interested in. So.
Yeah, so I've had a few experiences, but like very limited with as far as like microcontrollers and um I think yeah, this experience, like Adam said, it's been really interesting because being able to focus on a project like to this depth and getting that sort of like experience with a small person team has been like a lot more of a like learning experience, I guess, than being part of like a large robotics team or something like that that I have experienced in the past. Just because we all get that kind of hands-on knowledge, especially given that we have our own kits and we're able to work with it and sort of debug our problems as we go along with each other. So yeah, it's been a really great experience so far.
Amazing. Well, let's hear it for team one. Good job, guys. That was a great presentation. If you haven't filled it out, be sure to fill it out, the survey for team one, and then we're going to welcome team two to the floor. So whoever between John, Carter, and Adibola sharing the screen, I'll leave it to you.
Okay. All right. Let me just make sure this is good.
Okay. So we're team 2. I'm John Cates. And then there's also Adebola, and there's Carter. And this is our mid-program presentation. I go to CU Boulder, so I also major in electrical and computer engineering. So this project is very much up my alley. Very interested in the electric vehicle industry. And I'm really enjoying this internship and being able to learn about key components such as the CAN bus.
My name is Carter Sura. I'm a sophomore at UW-Madison. I'm from Racine, Wisconsin. I'm majoring in computer engineering. I applied to this to learn more about engineering and electric vehicles, and build relationships with other people in this profession.
Hello, my name is Adebola Babatunde Lawal. I'm a computer engineering major from Howard University. I applied to this program just to learn more about electric vehicles. I've always had an interest, and this was kind of out of my scope of, engineering, but I'm enjoying my time so far.
All right, so here's an overview of our project progress so far. Our code can receive and read incoming CAN messages of the data frame type and print out relevant information from those messages. We've tested our design on a breadboard and designed a full PCB and schematic of our product in KiCad. So we also researched and learned more about the methods used by Modine and others in the industry, electric vehicle industry, like the 8D methodology for design and the ISO 26262 safety standard. What was our design process? Our design process involved considering all of these industry practices and implementing them throughout the process. Certainly involved a lot of trial and error. For example, some of the challenges we faced were small mistakes in the wiring of our breadboard circuits, not being able to get the right library to work properly in the Arduino IDE. We had to work as a team to get around these problems, and we learned a lot about electric vehicle design from the program and from working together as a team.
So here is our prototype board. It's just the 2 transceivers and our Teensy board. In our full schematic, we also implement bypass capacitors, just because you're dealing with, instead of 3.3 volts, which is pretty low for bypass capacitors, 5 volts is a little higher. So being able to prevent surges is really important in protecting the transceivers and making sure that the data going through is good. Besides the capacitors, we also have terminating resistors on our schematic and on our prototype board. They're very small, but you can see them that they're right next to the CAN H and CAN L lines. Those are to protect reflections across the wires because they're connected. So by having terminating resistors, you can prevent interference between those 2 lines and make sure that those connections are good. Something that's nice about working with multiple transceivers and the CAN bus is that the wiring between transceivers is very simple. You just need CAN H and CAN L communication, and then you need to have at least one of them connected, or you then just have a wire going back to the main board to be able to communicate with them all. It's one of the important features of the CAN bus is the minimal amount of wiring that you need for a large system in order to be able to communicate.
Yeah. So the purpose of our code, as stated in the project brief, is to receive incoming controller area network or CAN messages and print out information from each message. So an evolved version of our code could be used in vehicle telematics to receive remote diagnostic data from a vehicle. How does our code work? It has 2 methods, setup and loop. In setup, we set the baud rate or the speed at which the Teensy communicates with the computer We configure the digital pins. The next part of our code is the loop method, which sets the parameters for our CAN message, like data length, message ID, and data types, and then sends that message to the teensy. It receives the data frame back from the teensy and outputs the information contained in that message to the serial monitor. The top left picture is our setup method. And the bottom right, what is it capable of? Our code can handle the data frame message type, which is a standard CAN message type. It's used for transmitting data to the other nodes on the bus. We can send or receive a data frame and print information to the screen based on the data received in that message. The second picture is an example of what our code would print. It's simple, but you can see it's communicating with both of the two CAN transceivers. This is the serial monitor. All right.
So I've already talked a little bit of the CAN bus, but it's one of the most essential parts of a vehicle to be able to communicate with each other. In just like a modern vehicle, you're dealing with 70 different ECUs that all need to be able to communicate with each other. And that only extends further when you're dealing with electric vehicles, because that's more electric parts. Oftentimes they're more luxurious. So you've got a lot more parts going on that need more ECUs. And by using the CAN bus, you're able to have a single ECU communicate with another ECU that's on the other side of the car and be able to request information about that ECU. And the CAN bus is able to allow that full network communication with itself. And then obviously our project is just a very simplified version of what a CAN bus network would look like in a car. We're obviously dealing with just 2 transceivers, but it's very scalable once you understand how to add additional transceivers on top of that. It's very simple to add 10 more, 20 more to be able to communicate with each other. You've already heard about the ISO standard, but it's basically a standard of application for something that, or all of the checks that you need to go through before you put something out for after development. Basically the safety management, hazard analysis and risk assessment, the safety concept, and then obviously the verification and validation of its safetiness. Obviously going forward, we want to implement better testing to comply with the ISO standard. So that includes using error frames and increased checking of the data to make sure that things that are coming out of the serial monitor are correct and that the timing of everything is correct. If we were to go even further, we would obviously try and test in different situations, such as weather and humidity, to make sure that our system is still able to work in less than desired conditions.
So for the next steps, we were talking and discussing how we would be able to develop a CAN scanner to be applied to the EV, and how do we administer user market research to determine where a need exists specifically. So my thought process is that we would probably go through the other companies and their existing products as well, and to try to make a comparison there. And also, finally, we would conduct engineering research in order to convince stakeholders that our final design is feasible and is useful and can be implemented in their own product. Thank you.
Ms. Keegan.
Yeah, I just want to say, nice job, everyone. I know you guys talked a little bit about like some of the challenges you faced, but was there anything that jumped out, kind of how you were able to run into something and maybe kind of work through a challenge? And then I'll kick it over to the Modine team.
Any challenges that other challenges we had to overcome? Um, yeah, just a lot of issues with just getting stuff to work, I guess. Yeah, I think we're all very new to this. Especially, I mean, I've had some experience with breadboards and stuff, but I've never designed a full PCB. So I'm still figuring out some of that in KiCad. Like, yeah, especially like the backwards wiring or backside wiring, like some other people were talking about. That was very new to me. But yeah, I don't know if anybody else in my team has any similar.
Um, if, oh, sorry, the question was what challenges we faced, right? I think I misheard, right?
Yes.
Oh, so personally, I had um, like I never really saw there before, so I kept making a mistake. So I had to kind of figure that out and like fix my mistake, and also the whole with the fact that I also didn't have all my materials, so I had to kind of have to work with what I had, and it wasn't a lot. I think personally, this although I am interested in it, this was like very confusing for the first time, but I'm really appreciative of the fact that I got to be a part of this, and I'm learning so much. But yeah, basically that's it.
All right, I got a couple questions too. Nice work on that presentation, by the way. Um, First of all, you're talking about for ISO 26262 again, doing like a hazard analysis and risk assessment. Do you have any actual plans to make one of those?
I think. Sorry, I was waiting for John. It's his slide, I think. Yeah. John, you want to jump in? Oh,
Maybe I'm mute there.
yeah, I can just say that we'd try to implement an airframe, or I mean, any testing we could do. Yeah, I mean, we'd probably have to get the board developed. So I mean, yeah, we don't have anything written down for any plans for ISO 26262 testing, but we'd definitely be interested in it to see what our board can handle. No, John, sorry, it's not. Yeah.
Okay, cool. Yeah, I asked because you can do some fun stuff with those. Like here at Modine, we're developing this valve, and we were kind of worried about what would happen if you would stick a finger in the valve while it was turning. So we're buying some ballistics dummies, basically, with like realistic bones. We're gonna stick the fingers on that into the valve and see if it can like cut off fingers. So I was just curious what kind of plans you had for figuring out what kind of hazards there are on a CAN scanner.
Yeah, nothing that cool. Just see how it responds to the its environment.
Okay, cool. You also mentioned telematics as a potential use case for this. Have you put any thought into what a telematics product would look like using a CAN scanner like this?
Yeah, maybe something that could, if it was like an aftermarket thing, it could like plug into an OBD scanner port, and you could I mean, like I know stuff like that already exists, but like it could be used for like just for maybe like for especially for like fleets of like vehicles. Yeah, like John's saying, they have for risk assessment and hazard analysis. Oh, is he? Okay, yeah, he's talking about the ISO. But yeah, you could use it to monitor like a fleet of vehicles. Like yeah, like just commercial. I think commercial would probably be the best use for it. Like yeah, truckers, maybe like a trucking company. Could know what the status of their vehicles while they're on the road. A lot of preventative maintenance.
Oh yeah, great answers there.
It's like,
Those are the questions I got.
okay. Good questions.
Thank you.
All right. Anything else then, or I guess we're okay. Thank you.
Yeah, great work. Thank you for the presentation. Again, I love the ISO 26262 references in here.
Yeah, thanks.
Yeah, and then Darius, for more information, the final presentation will be kind of more around that creative application, that those questions that you're kind of digging at. So the students will have even more time to research and develop some of their concepts for a cool creative solution.
Okay, great. I'm looking forward to it.
Well, awesome. Great job, Team 2. If you haven't done so already, please fill out the survey for Team 2 as we welcome Team 3 to the board. So Stephen, Trey, Gavin, and Charles.
All right, I'm pulling up the slideshow right now. Just to make sure, can you guys all see this?
Can see it.
All right, awesome. Well, as my team already, I can't really see your faces right now, but I'm gonna assume you guys are. So, just for starters, we're Team 3. This is gonna be our Modine Manufacturing mid-project presentation. Since there's 4 of us, it's kind of hard to fit on one slide, so we did 4 slides. I'm from a small village called West Alexandria, Ohio. I go to the University of Dayton, and I am an electrical and computer engineering technology student with a minor in automotive systems. Fun fact here on the very left side, this is my twin brother. And an interesting project I've done was that I created and printed a PCB for a binary clock that worked in part with a Basis 3 development board.
Hello, everybody. My name is Gavin Harwood. I go to the University of Wisconsin-Madison. Currently, I'm majoring in electrical engineering, and I'm planning on specializing in embedded systems. I'm from Seattle, Washington. I'm actually on an intramural soccer team, so that's a blast. And one interesting project I'm doing is I'm currently building an automated watering system for plants in my backyard.
Hello, everybody. My name is Charles Carroll. I'm a sophomore at the Columbus of Technology in Chicago. My major is in electrical engineering. Fun fact about myself, my level phone is double jointed, so I can bend it back pretty far. I'm not going to do that, but I'll save that for like another thing or something. But a fun project I assigned was we designed a mini traffic light system using Boolean logic and logic gates, so that a specific wave function. So, yes, clearly now.
Iffy.
It's a little like underwater. It might be like picking up a different microphone, but
Speaker. Sorry about that.
Trey, we also can't hear you. All good.
All right, well, while everyone's fixing their microphones and whatnot, just so you know, it is Gavin's birthday today. So if you get a chance, wish him a very happy birthday.
All right, how about
Happy birthday.
Thank you, everybody.
can you guys hear me now?
You're good, Trey.
We
All
can hear
right. I apologize for that. Yeah, so I guess I'll get into my slide here. So my name's Trey Vocone. I'm a junior electrical engineer at the University of Iowa. I'm from a small town of Chelsea, Iowa. Fun fact about me is that in middle school, I started the robotics or the first robotics team in my middle school, team FRC 12168. Interesting project that I'm currently working on is I'm designing a custom 3D printer from the ground up. Pretty excited about that. And I'm interning at Modine to prepare myself for a career in the EV field.
All right, to go through the process, obviously we've had 5 weeks. The first week, week 0, was kind of just us being able to figure out the team communication and figure out what times work for us because everyone obviously has different schedules. We also learned a little bit about the CAN bus and how the data was transmitted between the nodes. For our second week, or the first full week, we learned the fundamentals of everything going on and the basics of our teen CIOs. For our second full week, we started to build a small CAN bus on the breadboard. We got a better understanding of our hardware and we started implementing software. For our third week, we added on to the CAN bus hardware. So we added more things, we added more transceivers, and we also, added and refined a little bit more of the code. And now with week 4, obviously our presentation, which we will start with the hardware design. So with the KeyCAD design, it was a little hard to make the PCB, even though I've had understanding in that. We had a few problems, so we didn't include that. And I didn't want to include an image because obviously with the kits we were given, the wires are a little all over the place, and I wanted to make sure everything looked clean. So with the hardware design in KeyCAD, I made sure to color code everything. So on the right, there's a little legend. So obviously everything in the red is going to be our power. The black is going to be our ground. The green and blue are your CTX and CRX, which on here are labeled D and R. And then obviously the orange and purple would be how the CAN buses connect to each other and talk. So obviously the high and the low. Trey, you're muted.
Yeah, so obviously with all hardware stuff, there has to be software that powers it. So I'll kind of go over the brief overview. So our software design, our ultimate goal was to implement readable, organized, and effective code that could be a good framework for a future team to maybe take over. We wanted to design our code as modular as possible and make sure that we implemented scaffolding. So that's all of our code would be indented properly so to make it easier to read, easier to group things together. We also implemented status and indicator lights as kind of a hardware indication to show kind of what was going on the teensy board. Kind of just another level of a debugging tool or a status tool that we could go off of. We also implemented different serial print statements to both test, confirm, and receive information from the teensy board and the CAN network. We also made quite a bit of use of functions. This helped organizing everything and made our code writing a lot easier.
Yeah, so after we got the first and second transceivers working, our goal was pretty much to add a third transceiver. So to do that, we kind of reused statements from the previous 2 transceivers. So we utilized the read function, write function, as well as if statements to kind of filter the bus for those messages. And essentially, we kind of recreated that and we're able to declare a third transceiver inside the code. This was after we were able to successfully hardwire everything. And what we found was after there was an extra transceiver on the bus, messages went both ways. So sometimes messages were actually lost. And to combat this, we actually had each transceiver read and write twice to make sure that every specific message ID was eventually read and printed, so nothing was overwritten or lost. To do this, we kind of implemented different mailbox features and filters. So we had CAN1 filter for IDs 2 and 3 and so on. We actually had no filters on CAN3, so it could read every message on the bus. And this is because we were trying to get a remote frame to send across the bus. And essentially, we did this by having CAN1 write a special message that had a 3-digit ID, a length of 0, and an RTR flag. So CAN3 would filter the bus with an if statement, read it, and print out its ID in response. And we tried to get error frames to work in the code, but we were unsuccessful. So some of our future plans are we're planning to eventually implement that. And as you can see, here's some of our sample code. So you can see we kind of redeclared different CAN messages at the top. We actually poked around the GitHub library and found a specific class named flags and .remote. And we set that equal to 1, which is a Boolean true. So we had CAN3 filter for the message on the bus, as well as the ID, as well as that specific flag. And you can see that that message's ID is 3 digits long. And then you can also see our print statements at the bottom.
Now we're not hearing anything, Charles.
What about now?
Perfect.
Okay, so basically I'm going to be explaining to you guys the applications of the CAN bus system and how it can be used in our day-to-day lives. And I'm also going to be explaining a specific implementation of the CAN bus system using one of Modine's own products. So essentially the CAN bus system serves as a communication system that allows for centralized communication between multiple different ECUs in a electric vehicle. A good analogy I found on this is that the CAN bus can be thought of as the body's nervous system. So whereas the body's nervous system allows different body parts to communicate with the brain and send different information to and back and forth from the brain, same with the CAN bus system. It allows different ECUs to communicate with one another and to communicate with the sort of main unit of the electric vehicle. So Modine's eVantage thermal management system, which is the system I chose to give a sort of brief run through of, uses the CAN bus system to take in the external temperature and then use that temperature to sort of regulate the internal temperatures of the battery so the battery can operate at an efficient rate. Lastly, two important, I guess, distinctions to make is that we are using the classical CAN model. There's another one, which is called the CAN FD, which stands for flexible data rate. The two main differences between these two is that the classical CAN is stuck using 1 megabit per second, whereas the FD can use 2, 4, and up to 8 megabits per second. So to go back to the system that I mentioned in the previous slide, as you can see, the controller connects externally to the CAN bus system, and it can also be interfaced with the different ECUs throughout the vehicle. So if we have a temperature sensor somewhere in the car, I'm assuming, that then picks up a external temperature, and then the thermal controller or the master controller, which is the sort of intermediary device, sends a signal to the internal system of the thermal management system to then respond with a opposite temperature or to activate the cooling or heating process. Oh, one other important thing I wanted to note is that while the CAN bus is a communication system, it cannot directly control the internals of the management system. That's done through the master controller or thermal controller. So lastly, the standards and test slide. So one of the prompts for this slide was to use the actual ISO 26262 test. The data
that was kind of provided to us was rather limited. So we decided to go ahead and make our own mock ISO 26262 tests. Those consisted of three main things. So first we have our LEDs and multimeter, which we use to measure the current and voltage flowing through the three transceivers. Secondly, we use a decoupling capacitor to sort of prevent the effects of a voltage drop from affecting our three transceivers. Lastly, we use error messages for each loop of our code, so that whenever any of our transceivers wouldn't receive data, we would then receive an error message to then know that that transceiver needs to be either coded differently or the hardware implementation needs to be changed. Lastly, to kind of, I guess, tie all this back into the actual ISO 26262 standards, a framework that I looked at was the ASIL levels, which stands for Automotive Safety Integrity Levels. And this is basically a system that uses the severity or danger that an error that can happen in the system poses to the user or to the entire system overall. So firstly, we have level A being the lowest level or the least dangerous, all the way to level D being the highest level of danger. So for our system, a LED not blinking would be level A, since it's something we can fix easily, whereas a level D error would be something along the lines of burning our TNZ transceiver, which is something we can't really fix and also poses physical harm to the user. Thank you.
Unmute, Trey.
I know, it's a freaking mic, man. Yeah, so I'll kind of wrap up with some of the future plans, our team plans to incorporate. To help with the durability of our CAN network and controller, we plan to wrap the CAN high and CAN low wires around each other a little bit. This helps protect against outside frequency interruption and just interference from outside electrical noise. We also want to do a lot of troubleshooting on how to send error frames, and we want to incorporate that into our code kind of as well to properly read them and to properly send them as well. We kind of want to do a lot of looking into multi-node systems, how to make our code as flexible as possible to the different CAN networks that we can have. We have prototyped a basic network scanner that will scan through a range of IDs and report back which IDs are being used by nodes on the network. And then we also want to kind of come up with a list of different tests and things that should be tested on our CAN bus system in order to properly meet the ISO standards. But all right, so I think that wraps up our findings. Do you guys have any questions? Yeah, George?
Yeah, so you just mentioned about wrapping your CAN high and low wires. Have you looked into what the actual specification is for that?
No, I have not looked in too deeply about that, no.
Okay, so there is an actual specification for the number of twists per inch for that, for exactly what you brought up with reducing the frequency interruptions and all that. So if you want to look into that a little bit further, it's in an SAE J1939 spec. So
what you think the spec was again?
it's an SAE J1939.
All right, I will look into that. Thank you.
Yeah, I got some questions too. Again, great work on throwing the ISO 26262 stuff in there. I'm sensing a theme. I love to see that every time. So you're talking about some kind of error handling in your code. What kind of error handling do you do right now, and what are you planning?
The error handling that we have now is mostly just done through our indicator lights. The planning that we do have planned is being able to properly read the error frames. and being able to properly print those, the error out through the serial feedback. If
All
that
right.
kind of
I guess
answers your question.
I guess to kind of add on to that, we also are looking into being able to detect which ID is being used. So if there's a mismatch between the IDs, we can then outprint a message so they know that we have to fix that ID.
Cool. Nice. Yeah, you were talking about multi-node systems. What are your plans for how to handle those and display information from those?
Yeah. So we have code kind of prototyped right now. We're still kind of in the process of ironing out some bugs with it, but you enter in kind of a range of different IDs that you want to test, and the code will kind of loop through each one. It'll send a remote frame out. It'll send a remote frame request out, kind of asking that controller for some kind of information that it will then echo back. If the code, if the controller echoes it back, then the code will read that and then grab the ID of it and display the ID. So the general purpose of that is just to gather information on what all is on a network. So like the idea behind it is that, you would plug it into some mystery network. Maybe you're unsure all the IDs, or you're unsure of all the different nodes that are plugged into it. We thought it would be kind of a useful feature to both experiment with and maybe potentially use to be able to plug something in and then scan the network and get an idea of everything that's connected to it.
Nice. Yeah, that definitely sounds like a useful feature.
Any other
All right.
questions?
That's all from me, unless anyone has any more.
Well, awesome. Great job, Team 3. And good job to all the teams. This was an amazing turnout. It was great to see kind of from week 0 how far you guys have come. And it's great. It's been great. I can't stop smiling. So I appreciate all the effort and time that you guys have put into this, and know that the Modine team appreciates it. Good job fielding questions. And yeah, looking forward to working towards that new research topic for the presentation. Steven, raising your hand or trying to applaud?
This is an actual question this time. So do you or do you not want us to do a Google form for our own team?
You don't have to. We were kind of just doing it as a peer review for everyone who wasn't in it, but yeah.
Okay.
Good question.
Sounds good. I just wanted to make sure before I started zooming off to work real quick right after this call, and then you guys were like, "Why didn't you fill out the form?" And I was like, "What form?" Thank you.
All good. Well, awesome guys. We'll see you next week. Thank you for showing up.
Absolutely. Happy birthday, Gavin.
Yeah, happy birthday, Gavin. Nice job,
Yeah,
everyone.
thank you guys.
Thank you, everyone.
Everyone have a great night.
Take care, everybody.
Muted.